Okay, and we're back. Welcome back, everybody. This is going to be our second video in our functional analysis series. We're going to start, before we get into the contents of the book, I want to start reviewing some concepts from measure theory. Now, if you haven't seen measure theory before, that's okay. Um, this review is not going to suffice as a full course. We're going to skip most of the proofs, but you're welcome to do them. They might make some fun exercises. Um, so we're going to start our review anyway of measure theory with a definition, and that's going to be you've probably seen it before, but I just want to review it, refresh your memory, and that's the definition of a power set. We're going to lay out some definitions here, and for these definitions, we're going to let X be any set, finite, infinite, countable, whatever. Okay, and we define what's called, I'll use a different color for the name, the power set, which we write cursive P of X. This is given by the following collection. So P of X is the collection of all sets A such that A is a subset of X. That's it. So it's just the collection of all subsets of X. Okay. If you want a quick example, and we can do one. Let's say if X is equal to the set 1, 2, what is P of X? Well, this is quite easy. All we have to do, going back to this definition, okay, the power set of X is the collection of all subsets of X. Okay, so what are the subsets of X? What can we take out of X? Well, we could take out nothing. Okay, so that's the empty set. So the empty set is a subset of X. So let me write P of X here. And we can start with the empty set. Okay, what else? Well, I can take out 1. Okay, so the set containing 1 is a subset of X. Okay, and I can do the same with 2. And of course, X is a subset of itself, so I can put X there. So 1, 2. And that's it. That concludes the power set of X. So what we're going to do over probably the next couple videos, we're going to be talking about subsets of the power set. Okay, so when I write, something that looks like this, sigma, capital sigma, is a subset of P of X, you should know and you should immediately identify that, know that sigma is a collection of subsets of X. Okay, so if I say if A is in sigma, right, you should know that A is a subset of X. Okay, so if I can equivalently write, okay, I can write either I can write A is an element of the power set of X, or I can write A is a subset of X. I like writing it like this, so I will write it this way. But just again, I'm just putting this as a review. Maybe you forgot the definition of a power set, or this is so you know the notation I'm going to be using. Okay, cool. So the next definition number 2, is we're going to be talking about a special subset of the power set of X. So we're going to be talking about a special type of collection of subsets of X. And I'm going to write it this way. So a subset, we're going to call it sigma. A subset of the power set sigma, a subset sigma of the power set of X is called a sigma algebra. Use a different color here. Is called a sigma algebra over X if we have the following three conditions. The first one is that the empty set and X are elements of sigma. That's the first one. The second one, the second condition, you can call closure under complementation. Closure under complementation. Okay? Meaning I can take complements and I remain inside the set. Let me scroll down here. Meaning, if A is an element of sigma, then a complement, which I define as X take away A, is an element of sigma. So if this black box is X, and this right here is A, so if A is in sigma, then also its complement, which I can put here. I know you probably know what a complement is, but I just want to, set the pacing a little slower right now while we're just opening up the subject. So this is a complement. So I'm saying both if I'm given that A is an element of my sigma algebra, sigma, then necessarily a complement needs to be an element of sigma. So that's my second condition, closure under complementation. And my third and final condition is that if I am given a sequence of elements in sigma, and remember this, elements of sigma are sets. So I'm given a sequence of sets. So if an from n equals 1 to infinity, this is a countable collection of sets, is a sequence in sigma. So I'm just going to write that. What that means is that an is an element of sigma for n is equal to 1, 2, 3. If I'm given the sequence of elements in sigma, then the union of all elements in this sequence, all of these sets, then the union of all of these sets is also in sigma. Okay, so you can call this closure. We can call this closure under countable unions. Okay, and that's the definition of a sigma algebra. Okay, so just to review what we've covered so far, a sigma algebra over X is a subset of its power set. So a subset sigma of the power set of X is called a sigma algebra if it satisfies three conditions. The first, it contains the empty set and X. The second is that sigma is closed under taking complements. Namely, if A is an element of sigma, then its complement with respect to X, a complement, is an element of sigma. Okay? And then finally, if I am given a countable collection of elements or a sequence in sigma, meaning that each element of the sequence an is an element of sigma for all n, then we must have that the union of these elements is an element of sigma. Okay, so sigma is closed under countable unions. Let's look at some examples of sigma algebras. So the first example of a sigma algebra, and the easiest one to understand, is of course the power set of X. So given any set X, its power set is a sigma algebra. And I encourage you to go ahead, pause the video, and try to prove it yourself. And we will do so here. So to prove that the power set of X is a sigma algebra, we need to first verify that the empty set and X are elements of the power set. So we'll just look at condition 1. Is it true that the empty set and power set and the empty set and X are elements of the power set of X? Well, if you literally write the definition of the power set, right? The power set of X is all sets A such that A is a subset of X. So to verify this, we just have to ask ourselves, Is the empty set a subset of X? Yes. So the empty set is an element of the power set. Is X a subset of itself? Yes, so X is an element of the power set. So this one is good. Let's verify the second condition. If we are given that A is an element of the power set, is a complement an element of the power set? Again, going back to the definition, all we have to ask ourselves here, if I'm given a subset of X, is its complement with respect to X a subset of X? So, is it true that X minus A is a subset, of X? Well, this is clear by definition of set subtraction, because X minus A, or a complement, you can write, this is defined as all of the elements of X that are not in A. Well, all of the elements of X that are not in A are elements of X. So therefore, a complement, which is X minus A, is of course a subset of X. Okay, so we get our second condition. And then now for our third condition, which is closure under countable unions. So if we have a countable collection of sets, or a sequence of sets in sigma, I can write it like this. If this is a subset of P of X, right? Because you can view this as a set. This is a collection of sets. And this is a collection of sets. So I can talk about a collection of sets being a subset of another collection of sets. So if we have a sequence in P of X, is the union of these sets an element of the power set of X? This is to ask, if I have a sequence of subsets of X, is their union a subset of X? Well, this is by definition. If I have an element of this union, if I have X in this union, then there exists some K, right? I'll just write it. So if X is in the union here, this is by definition, then I'll just write it like this. Then for some K, we have that X is an element of AK. But we said that this sequence lies in the power set. So every element of this sequence is a subset of X. So necessarily, AK is a subset of X. So X is in an element of X. Okay? So therefore, this union is a subset of X. And because it's a subset of X, it's necessarily an element of the power set. So therefore, we get the third condition. So this is the easiest example of a sigma algebra. So given any set, the power set of that set is necessarily a sigma algebra over that set. This is also the largest sigma algebra you can have over a set. Let's look at a second example of a collection of sets and ask ourselves the question if it's a sigma algebra. So I'm given this following collection of sets. Cursive A is equal to all subsets of R that are either finite or their complement in R is finite. Again, R right here, this denotes the real line. And so let's ask ourselves the question and investigate, is this collection a sigma algebra over R? Going back to the definition of sigma algebra, we need to verify three conditions. So let's test the first one. Is the empty set and R an element of A? Well, let's see. Is the empty set finite? Obviously. Okay, so the empty set is an element of A. We get that one. Is R finite? Is the real line finite? Obviously not. the real line is uncountable. Now, is its complement finite? Well, the complement of R in R is the empty set, which is finite. So this one's true because the complement of the reals, which is the reals take away the reals, is the empty set, which is finite. Great. Okay, now what about the second one? Is A closed under complementation? Is A closed under complements? So how do we verify this? We just take any element of A and we see, okay, is its complement also an element of A? So I'll maybe use a different letter. So we'll say let B be an element of A. So by definition of our collection, either two things are true. Either B is going to be finite or its complement will be finite. So we need to consider both cases. Okay. So case one, I'll just write case one, which will be suppose B is finite. Well, if B is finite, now we need to consider its complement. So consider B complement. So what we have to verify is, does B complement satisfy either of these two conditions? Okay. Well, if B is finite, well then B complement, we know that will be infinite. But for B complement, if we take its complement, what do we get again? Well, we get B, and B itself is finite. So that's literally just saying B complement, which is B, is finite. And with how we've defined A, right, since B complement is finite, then B complement is in the set. So B complement is an element of A. So that holds. Okay. Now the second option for B is that B complement, so suppose B complement is finite. Well, this is literally just the same thing that we're getting as far as it's a parallel proof here. So if B complement is finite, then B complement, right? Well, that's going to be infinite. But if I take that complement again, right? Just replace B complement with B in the above proof, and it's the exact same proof. Well, so this is finite. So therefore, and you know, so B complement is an element of A. And we've covered both cases. Okay, so A is closed under complementation. Let's see if we can take this home and determine if it's closed under countable union. Well, let's see. If I take the countable union, right, countably infinite union of finite sets, will I get a set that's finite? Well, obviously not, right? But could its complement be finite? Not necessarily, unfortunately. So this does not hold. And the case to consider would be, you know, just take, I don't know, take the following set. Just take the following set of integers n, you know, n equals 1, 2, 3, blah, blah, blah. Okay. So, oops, let me write it like this. Just take the sequence. Oops. Okay, just take the sequence of singletons n for n, 1, 2, 3, blah, blah, blah. Okay. So the union going from, I guess n equals 1 to infinity of this collection, that's going to be the natural numbers, right? Which is the set 1, 2, 3, going on to infinity. Okay, well, this is not finite. maybe I'll use a different color to emphasize that, not finite. But is its complement finite? Maybe we can hold out, we have some hope. But our hope is quickly crushed when we realize the complement of this is not finite, right? If we take the complement of that, so if I take union that complement, what I will get is the following. I will get this, the open ray from negative infinity to 1, union with the open interval from 1 to 2, union with the open interval from 2 to 3, union with blah, 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 the, in general, open interval from n minus 1 to n, continuing. And obviously, just by the fact we have an open interval here, which itself has infinitely many elements, this by itself is infinite. So it does not hold for the case of our sigma algebra here, that, for our collection of sets here, that it's a sigma algebra. While it contains the empty set in R, while it is closed under complementation, it is not closed under countable union. And then finally, let's determine if this collection of sets is a sigma algebra over R. So we're given a collection B of subsets of R, and it's the collection of open subsets of R. Just to review, since we're in the mood for reviewing, what's an open set or an open subset of R? And I'll use a different color. We'll say that A is a subset of R. This is open if for all, given any point in A, so for all points P in A, there exists some epsilon greater than 0 such that you could call it the epsilon ball around A. So you can say P minus epsilon, P plus epsilon. This is an open interval, is a subset. Is a subset of A. So this is what it means for a set to be open. And we're asking the question, is the collection of these sets a sigma algebra over R? And all, again, what we have to do is just check the definition. Is the empty set in R closed? Open. Are these open sets? Well, the empty set, I think you would use the word pathologically, is open. So the empty set is open in the reals. And the reals is open in itself, right? Given any point of the real line, any epsilon ball, right, which is an open interval, is going to be a subset of the real line. So this collection satisfies the first condition. And it fails at the second condition. You can probably already see it already. Is the complement of an open set an open set? So closure under complementation. Okay, is this set closed under complementation? Obviously not. Let's take any open set, right? You can just take, 0, 1. This is an open set. Is its complement open? No. Why? Because the complement is going to be from negative infinity to 0, including 0, union with the closed ray from 1 to infinity. This is not open. Why? If I take, using this definition, if I take the point 0, and I consider this open ball around 0. Let's say, negative epsilon, epsilon. Let me draw a picture to illustrate what I mean. Okay, here's 0. And this set in question is this closed ray shoots off in this direction, and then we have this same story at 1. We have this closed ray that goes off in this direction. Okay. The reason this set is not open, if I take this point at 0 and I consider any epsilon ball around it, okay, and it would look like this. No matter how small I make this ball, right, it'll never, let me use a different color for this. It will never, no matter how small I make it, it will never fit in to this set here, right? So therefore, we have an example of an element of this set whose complement is not open. So while this does not work, the third property actually holds, which is closure under countable unions. And this is a good exercise to do. I won't do it here, but I recommend if you are new to these definitions of open and closed, I recommend you do it. So this collection of sets is closed under countable unions. Why? Because we know that, this is from analysis, that any union of open sets is itself open. So while with this collection, it contains the empty set and R, and it's closed under countable unions. It's not closed under complementation, and therefore it's not a sigma algebra. But the question arises because if you are familiar with topology, it would be nice to encapsulate the topology of R, and if you don't know what that means, that's okay. But it would be nice to encapsulate in some way the topology of R, because it has some really, open sets are very nice sets to work with. It would be nice to encapsulate that inside a sigma algebra. And so, as it turns out, what we can actually do is create a wish list of sorts of what we would like our sigma algebra to include. What are the nice sets we want in our sigma algebra? And just based off that, we can generate a sigma algebra just based off what we want. And that's what we will cover in our next video. So when we come back, we will look at how to generate a sigma algebra given a collection of sets we would like to be in that sigma algebra.